Hello everyone and welcome to today's webinar, which is brought to you by Sartorius BIA Separations in partnership with AZO Network. Today's webinar is titled AAV Upstream Empty Full Capsid Optimization using CIM SO3 multi-well plates and mass photometry. A big thank you to the team at Sartorius BIA Separations for making this event possible. We're going to get started in a couple of minutes, but before we do, let me introduce today's wonderful speakers and explain a little bit about the format for today's webinar. Today's webinar will run as two parts, a presentation and an audience Q&A session. The first of today's fantastic speakers and getting us started in just a moment will be Henna Divanovic. Henna is an application scientist with a background in cell and gene therapy process development. She joined Refeyn in 2025, focusing on developing applications for cell and gene therapy. Throughout her career, she has worked on downstream process optimization, actively using mass photometry to support process development. Henna is joined by Marco Nairobi. Marco is a molecular biologist. He joined Sartorius BIA Separations in 2020 as a technical support professional. During his career, he's gained deep technical understanding of monolithic chromatography and clients' needs. As a product manager, he covers Sartorius BIA Separations high-throughput solutions. A big welcome to you both today. Before getting started, we have a few points about how to get the most out of your experience today. Firstly, the event is being recorded and we will share the on-demand link with you within the next 24 hours. So if you enjoy what you see or you have a colleague or peer who may benefit from seeing the content as well, please do share that recording with them when you get that email. Refreshing your browser normally resolves technical issues, but if this doesn't work, send a message using the Q&A box and our backend team will get you back up and running as soon as possible. As I mentioned, there will be a Q&A session following the presentation, so please send those questions in at any time and we'll get to as many of them as possible following the presentation. A quick note that if you are watching this back on demand, then you can still ask your questions, but you will receive an answer via email. Now let's get things started with the presentation. Henna, over to you.
Hi, thank you for the introduction. I'm Henna, application scientist from Refeyn, and today we'll be talking about AAV6, upstream empty full capsid optimization using CIM SO3, multi-well plates, and mass photometry. I will explain the importance of product purity and then go into mass photometry review. What is mass photometry and how does it compare to the other methods? What are regulatory considerations in this process? And how can you use mass photometry to optimize AAV production at every stage? So why is product purity important? So critical quality attributes are defined for a reason, and they're essential for meeting regulatory requirements set by agencies. There are a few defined critical quality attributes by regulatory agencies that include purity, potency, safety, identity, and content. If critical quality attributes are poorly controlled, they can cause failures in clinical trials and have potential safety concerns for the therapy. For AAVs, one of the critical quality attributes that are clearly defined is purity, and that as a part of the purity, we measure capsid content, or the ratio of empty capsids that do not contain DNA material, partial capsids that contain truncated DNA, and full capsids, which is our target and what we want to see, capsids that contain genetic payload. Problem occurs because empty AAV capsids and the partial capsids compete for the same cellular entry as full capsids, and that could reduce transaction efficiency. Moreover, there are several studies that have proven that empty capsids and partial generated during AAV production could have a negative impact and induce immune response, but also by having more empty capsids during the production, that could potentially raise production costs because the additional purification steps need to be introduced. As discussed earlier, the presence of these undesired AAV capsids can impact both potency and immunogenicity. That's why it's important to precisely quantify the amount of empty and partial AAV capsids in the product. Also, the right analytical tool will provide us with the right information around the process changes or the process optimization and how the product quality and changes over time and how that could potentially influence safety and efficacy. So by having the right analytical tool, this also supports improved process controls from development stage up to manufacturing. So how does that ideal analytical solution look like? So ideal tool will provide us with results in a matter of minutes. It'd be able to quantify the content accurately, the content of empty, partial, full, and overfilled capsids. It consumes only low volumes of samples. It's easy to run and serotype. It is serotype and agnostic and is applicable throughout the whole process at the different purification stages. Now, how does mass photometry fit into that picture? Let's have an overview what mass photometry is and how does it work. So mass photometry is single particle analysis. So when you analyze a solution that contains AAVs, and when you put that solution on the glass slide, that is then illuminated by laser, AAV capsid scatter the light. An interference of the scattered light and reflected light produce something that is known as a contrast. So the magnitude of contrast, or the higher intensity of the contrast, the heavier are those particles. It's directly proportional to mass. So to be able to convert that contrast then to mass, we need to use our calibrant mass reference B2 of a known mass and convert our measurement into mass. And you end up with the output that looks like a plot on the right-hand side, where you can clearly distinguish different populations of AAVs, including empty, partial, and full capsids. So how SAMX MP, that is how mass photometry instrument, fits into the picture of an ideal analytical method that could be used across process optimization and manufacturing. It does require a limited sample preparation. It is a label-free measurement that provides very results very fast. So in less than 5 minutes, you'd be able to have your results, including acquisition and the data analysis. It does consume a very low amount of sample, only 10 to 20 microliters, and it's extremely easy to use with very user-friendly hardware and software. We can enable training of the operator in less than a day. If the company requires automation, sample analysis could be automated, where 24 samples can be tested in less than an hour and a half. So considering a very high price of the gene therapy, it is very beneficial to have an analytical method that is inexpensive, and to run one sample, one AAV sample, it costs less than $5 per measurement. How does mass photometry compares to other methods? So there are now multiple research articles that are released, but this is just one of the examples of the data set that is available, where mass photometry and different serotypes in this case were compared to traditional methods, including transmission electron microscopy and analytical centrifugation. And we can see that the results from SAM-XMP have a really good agreement with both of these methods. This is just additional data set where mass photometry, again, different serotypes were compared to analytical ultracentrifugation. And we can see a really good agreement on all populations of AAV that are present in the sample, including empty, partially filled, full, and overfull capsid. Gene therapy for a long time lacked good reference controls. And this is really important because it could potentially lead to inconsistent assays. Establishing the assays and then running those assays, it could lead to not having consistent controls across the manufacturing and potential batch failures because of the inconsistent controls. So by establishing appropriate reference standard, we can support process validation and ensure batch-to-batch consistency and meet all the regulatory expectations. So US Pharmacopoeia has recently released a reference standard that facilitates process validation and batch-to-batch consistency. This is AAV8 empty and full standard. And for the release of this reference standard, they use mass photometry alongside other orthogonal techniques. And they have proven that mass photometry can reliably measure empty and full standards alongside SECMOLS, CDMS, AUC, and Solar VP. But moreover, because of the lack in general of the reference control and official guides, US Pharmacopoeia has also recently released Gene Therapy Analytical Guide, where they included mass photometry as a method to test AAV capsid content and as a method for the process characterization and QC release. Again, now a quick overview of SAM-XMP and SAM-XMP Auto mass photometry instruments that could reduce the operational and analysis costs by offering very reliable measurements. And they are a complete solution for all the serotypes because they're serotype agnostic. But moreover, they could be used in the GMP environment as a QC release method, and the software is compliant with GMP regulation or with the 21 CFR Part 11 guidance. Hardware and software are very intuitive to use with a possibility of the automation. How could mass photometry be used to process optimization in every stage? So the goal of the every optimization is to achieve the maximum productivity and purity, but with the least amount of steps and driving the minimum costs during that optimization. Optimization usually includes upstream and the downstream process optimization. In the upstream, yields are very important, but sometimes the capsid content could be overlooked. While in downstream process optimization is important to deliver the process that is not expensive by avoiding the product losses, but at the same time ensuring that the purity of the product is really high. Once upstream and downstream optimization are completed, then we can use mass photometry to assess the process robustness and batch-to-batch consistency. So usually during the upstream optimization, the aim is to have the high-throughput studies, and they are predominantly DOE studies where multiple parameters are being tested. And as a result, multiple samples are being generated. So now there is always a choice of method, but that method could potentially introduce bias just towards one parameter that could potentially negatively affect other parameters. Researchers usually tend to choose tighter in the upstream optimization as their primary goal. But just by choosing tighter, they often overlook purity or the capsid content. So ratio of empty, partial full, and overfilled capsid is not always in the focus during early in the optimization process. So this could potentially increase the complexity in the further purification steps. So the higher content of the empty capsid, the harder downstream purification is. So mass photometry is an ideal method for the upstream optimization, considering how cheap it is. It is suitable for screening multiple conditions in different formats just by having a minimal purifications, whether these are multi-shake flask studies, under 15 or multiple bioreactor runs. Researchers are also able to fine-tune the parameters and assess how they impact AAV full and empty ratio. But is also, as an outline tool, it is possible to assess scale-up efficiency of the process. And how does mass photometry compare to the other methods that are being used in upstream optimization? So considering that these DOE studies are usually performed in shake flasks and the amount of material generated is precious, having a method that is only going to consume 10 to 20 microliter makes mass photometry suitable for analysis. So just imagine the timeline, the cost, and the quantity of material that is required for AUC at this level. A lot of analytical methods require comprehensive training, while mass photometry takes less than a day. It only costs less than $5 per sample and also reduces operational cost because it is extremely fast method. Other methods are often focused on one output, and mass photometry provides a comprehensive data set, and all of AV populations are available as an output, including empty, partial, full, and overfull AAV data. The crude lysate contains a lot of impurities, which usually prevents the resolution of AAV capsids. That's why the minimal purification is required to be performed for mass photometry analysis in these samples. So there are multiple purification methods that could be used in this process, including CIM SO3 monolithic weld plates and different affinity ligand magnetic beads or resins. There are already several publications available that demonstrated a successful and minimal purification of crude lysate and then testing these parameters using mass photometry. So as mentioned, to achieve a desired level of purity of samples from mass photometry and have an insight into upstream process, we could utilize bioseparation CIM SO3 weld plates. So now consider a price. Mass photometry is an inexpensive method, and when that is paired with reusable, fast, and inexpensive method for minimal purification, that could provide you with the valuable, if not very crucial, insights into your process. So there are many different AAV serotypes that could be used for different therapeutic purposes. And a lot of methods are usually very specific to the serotype. So both monolithic weld plates that are used for minimal purification and mass photometry are serotype agnostic. So there is a possibility to do the optimization of multiple AAV serotypes at the same time, but test them during the same run with a minimal purification and mass photometry. And to speed up this process, it is possible to fully automate purification as well as testing. So together, monolithic plates and mass photometry do offer a fast, cost-effective, and a serotype agnostic solution that can be further accelerated through automation. Thank you, and now I will hand over to Marco.
A nice presentation. I'm Marco Norbe, product manager for our plate format here at Sartorius BIA Separation, and I include you how we use our CIM SO3 plates with Refeyn XMP to optimize our AAV6 production process. So I'll start with what are monoliths. This is the technology behind our monolithic plates. I'll continue how we develop a universal protocol for AAV upstream samples, and I'll finish off with how we use this protocol alongside with CIM XP to optimize our AAV6 production process. To start off, convective interaction media, the trade name that we call our monoliths, is a chromatographic media made as a single unit structure that is highly interconnected with convective channels that are evenly distributed throughout the entire bed. Those channels come in three distinct sizes: 1.3, 2, or 6 micrometers in diameter, and we choose the appropriate diameter depending on the size of the target molecule and the application we are doing. On the picture above, you can see a thin micrograph of monolith, and we can pack this monolith in different formats. We can pack them in analytical column format, in preparative column format, or in well plate format. And on the right, we can see an example where we pack our monoliths in a multi-well plate format. So 3 wells, where on the bottom we have a frit that offers support to the monolith. This is where the purification happens. Above the monolith, we have the sample well. This is where we put our sample, and we elute our sample at the bottom with vacuum, positive pressure, or centrifugation. If we take a closer look inside our monoliths, we will see that every channel is connected to 16 other channels. There's no dead end pores inside the monolith, meaning there's no entrapment of your target molecule in it. If we do chromatography, we will see that we can use high flow rates due to even flow distribution and low pressures. And the entire surface area of the monolith is accessible for binding of your target molecule, meaning we get high binding capacity. This gives monoliths transport characteristics we can use in our purification process, regardless upstream or downstream. The flow through the monolith is convective, meaning if you do chromatography, we get sharp peaks. Resolution and capacity are flow rate independent, meaning we can use high flow rates and have fast processes. If you pack our monoliths inside the plate format, you can get them in wide ranges of chemistries, like anion exchangers, QA, DAE, cation exchangers, SO3, COH, different hydrophobic, hydrophilic chemistries, different mixed mode chemistries, affinity chemistries, reverse phase chemistry, or different activated chemistries. We offer 3 different monolith sizes with our plate format. So we offer 2 96 well plate formats, one that has 0.05 milliliters of monolith inside each well, the other that has 0.2 milliliters of monolith inside each well. And we also offer 24 well plate that has a 1 milliliter monolith inside each well. We choose the correct monolith size depending on the sample volume that we want to purify, and also on the amount of target molecule that we have in our sample. The plates are made according to ANSI standard, meaning if you have a liquid handling robot, you can easily automate your processes. If you do not have a liquid handling robot, you can operate them manually with vacuum manifold, positive pressure manifold, or a centrifuge, depending on what you currently have in your laboratories. I'll continue with how we develop our protocol and how we use it to optimize our AAV6 production process. So we have an upstream lab in our facility, and we also talked with our clients that do AAV upstream optimizations. And we saw that a few challenges arises when you do an optimization. So we saw that not many analytical techniques are compatible with crude AAV harvests. The sample, the titers in our upstream can be low. And the crucial thing is we need to see our empty and full ratio. So we went behind our drawing board and we set goals that we need to achieve for our purification protocol. So to, let's say, efficiently purify and concentrate our AAV sample that is compatible with different upstream analytics. The protocol should be applicable to any serotype, even chimeras or engineered capsids, or the capsids where we are currently lacking method. The protocol should be fast, and it should support high throughput processing and automation, so the plate format. Developing the protocol, we based it on our CIM SO3 plates. The SO3 chemistry, because we already showed that it can capture any AAV serotype, and plates because we wanted to do many samples at once in a high throughput format. So we developed a purification protocol where we can quickly purify and concentrate our upstream samples to be applicable to analytics, to upstream analytics where certain purity and concentration is required, like mass photometry, dPCR, ELISA, CGE, AUC. The protocol is fast. We need less than 3 hours from crude harvest to purified samples, regardless if you purify one sample or if you purify 96 of them. The plate supports high throughput processing and automation. And once you're done with your protocol, you can clean the plate with sodium hydroxide and store it till the next run. So how does the protocol look like? So on the left, you see a schematics how it looks like. So we take our AAV lysate, we acidify it to pH 3.5 to prepare the sample for binding and do a quick clarification with the centrifuge. We load our supernatant to the preconditioned plate and wash the plate with binding buffer to remove any unbound impurities. Then we have two options for elution. One is a multi-step AAV elution at neutral pH. The other is a single-step AAV elution at slightly acidic pH with high salt. We choose the appropriate elution based on our AAV and the analytics we will perform. So we did our single-step AAV elution. After it, we need to neutralize and dilute our samples, so to elevate the pH and lower the salt concentration, or we can simply do a buffer exchange into our formulation buffer, and we have our sample prepared for our analytics. On the right, we have two histogram overlays made with Refeyn's SAMUX MP, and here we can see the beauty of this protocol. In the histogram in front, you can see a sample before SO3 purification, and it's so full of impurities that we cannot discern what is inside. So in the histogram at the back, we see a sample purified with CIM SO3 purification, and we can easily discern our empty and full ratio because we removed so much impurities. I will continue with how we did our AAV6 upstream optimization. So on the picture above, we can see how we did a single experiment, how we first grew our cells, how we transfect them, how we added feed, and after our cells grew, we lyse them and then do purification on our plates and analytics on SAMUX MP. The plates and the SAMUX are quick, so we can rapidly go back to our bioreactors and optimize our run to further improve our production process. On the picture below, we can see how the whole process looked like. So first we did our lysis screening to check where our AAVs were. Here we saw that the best combination was with salt and detergent lysate. Then we went to screen our media to see where the cells grow the best. Then we did our first design of experiments where we optimized our transfection, and then we went into our second design of experiments where we optimize our plasmid ratio, and this concluded our optimization process. Every other week we did analytics where we measured virus starter with dPCR and percent full with mass spectrometry, and these were our two criteria to continue into the next step. For our media screening, we evaluated two medias, NX media and MB media, both in batch mode and both with an additional feed. On the picture on the graph below, we can see our results, where the bars represent the titer and the dots represent the percent full. The titers range from 2E10 for the MB media and to up to 1.6 to the power of 11 vector genomes per milliliter for the NX media in fed batch mode. Percent full range from 22 to 25% full, with one sample that was below limit of detection. Here, because the percent full was relatively similar, we choose to continue with the media that gave us the highest titer, so NX media in fed batch mode. And on the right, you can see the sample that was taken for further optimization that was measured on mass photometry. After we optimized our media, we went into our first design of experiment. This was done with MODES software, and the factors that we were looking at were cell density at transfection, plasmid amount, and ratio between plasmid and transfection reagent. The MODES software proposed 17 experiments that we did in shake flasks, and the responses that we were looking at were AAV titer measured with dPCR and percent full measured with mass photometry. The results, you can see them in the bars in the graph below. So the bars represent the titer and the dots represent the percent full. The titers range from 5E10 to up to 2E11 vector genome per milliliter. The percent full range from 9% to 30%, and we also had 3 samples where we were below the detection limit. And on the right, you can see a histogram made under condition 1 that was purified with our plates and measured with mass photometry. So all of those results were analyzed with MODES software, and it gave us 2 heat map of predictive results. So one heat map for titer, the other for percent full. So here, the colors on the heat map, the red represents higher or better, the blue represents lower or worse. So for the vector titer, the higher amount of plasmid we use and the higher amount of transfection reagent we use, the higher the titer. With the percent full, we can see the lower amount of plasmid we use, the higher percent full. And the MODES software then proposed an optimal set point to use that gives us a balance between the highest titer and the highest percent full. Taking these results, we went into our second design of experiments where we optimize our plasmid ratio, so ratio between rep cap, gene of interest, and helper. And the MODES software proposed 15 experiments you can see in the design space visualization which those experiments were. So 3 edge points, 3 times the center points, and 9 points in between. And we did those experiments in our Amber 15 to showcase the high throughput capabilities. On the right, we can see the graph representing the results, so 15 results. Here, the percent full was already higher, so it ranged from 21 to 38%. Here, the titers were a bit lower. This could be due to the difference between shake flasks and amber, but this could also be optimized. Analyzing all of these results with model software, first on the left we see an example of a sample analyzed with Samux MP that was purified with CIM SO3 plates. On the right, we see 2 heat maps, one for titer and one for percent full. With percent full, we can see that the more RepCap plasmid we use and the lower amount of gene of interest we use, the higher the titer. With percent full, we see the higher amount of gene of interest we use and the lower amount of helper we use, the higher the percent full. So model software proposed an optimal set point to use, and this optimal set point led us to results of 1.8 to the power of 11 vector genome per milliliter and 30% full of AAV. In conclusion, we can see that using our CIM plates and Refeyn mass photometry proved to be a valuable tool for our AAV6 production optimization process, where we managed to improve both vector titer and capsid ratio. And the complete optimization process took us 8 weeks. So CIM SO3 plates combined with multiple analytical tools enable you rapid insight to help you improve your AAV upstream process. I would also like to thank my colleagues. So first, Moica, Victoria, Maya from our downstream lab that have developed the protocol, my colleagues from Upstream Analytics Lab, Petra, Melita, Sandra, Jana, and Ivana, that made this optimization process and that made also this webinar possible, and our partners from Refeyn, Hina, Svaya, and Jacinta. And now we will go to our question and answers team.
Hello everyone, we're going to start the Q&A now. Just a reminder that you can send your questions in by the Q&A box on the right hand side, so please send your questions and we'll get to them. But we have got a couple to kick us off. The first question is, how many times can I reuse the plate?
So how many times we can reuse the plates will depend on your sample and how well you clean the plate. So the dirtier the sample, the less often you will be able to use the plates. So the dirtier the sample, the less often you will be able to use the plates. But you can clean them with 1 molar sodium hydroxide and then store it till the next run. So this is all written in our instructions for use document.
Yeah, and on that, just a reminder that we have got all of the handouts in the handout section, so do remember to download those before you leave us today. On to the next question. With how many AAV serotypes was the protocol tested with?
So the protocol was tested with, so when we developed the protocol, we tested it with our internal samples that were AAV2, AAV8, and AAV9. Our beta testers also tested it with AAV5. And with this optimization, we show that it is also possible with a challenging sample of AAV6.
Thank you. Another question we've got here. Do we need to test AAV capsid ratio during upstream optimization with multiple methods?
I can get this question. We've seen that mass photometry agrees very well with other methods like AUC, CDMS, and SECMOLs. So consider how easy is to use mass photometry and how cheap it is, and then you'll get the same result. So to test the ratio, there is no need to use multiple methods in this case. Just plug it on CIM SO3 columns and then test it on SAMX.
Thank you. And a question here, are the same buffers used for each serotype?
Here, so yes, we have two options to use. So one is with one where there's a elution with slightly acidic pH and a high salt, the other is at neutral pH, and all the buffers are listed in the protocol and you can use them. So the method were tested with the same buffers, the buffers that are written in the protocol.
Thank you. I think that's all of the questions we've got time for today. Like I've already mentioned, make sure to download the handouts before you leave us. If you do have any questions and we haven't gotten around to answering them, then please still ask them, especially if you're watching this back on demand as well. You will receive an answer via email. On that, this webinar will be available on demand. So if you're wanting to watch anything back, then you are able to do so. You will receive notification as soon as the webinar is available. With that, we'll just say thank you so much for attending the webinar today, and we'll hopefully see you for the next one. Thank you.
Thank you.